Am I audible? Hello?
Yes, sir.
Okay, fine. So we are going to start our session, today's session. Uh, so uh, in the previous session, we have actually loaded some of the tools onto the tool magazine, uh, but they are not actually measured. They are just loaded onto the tool magazine. Now in today's session, we'll be using some measuring system by which we measure the length and the radius of different tools so that we'll be able to perform some machining operations. So in today's session, first we'll have a topic on measuring system. Then we'll have a look on the work offsets. The We'll understand the concept of work offsets. What are the different offsets that are and we'll see how we can set these work offsets. What is the procedure and all other related topics will be covered in today's session. Then we'll also uh, cover the clamping of the workpiece onto the table, and after that, if we have time, then we'll go for machining operations as well. So let us start uh, with the measuring system setup. So actually, in previous section, we just loaded the tools onto the tool magazine, and today we are going to measure these tools with the help of our measuring system that's called Bloom. So Bloom is actually a laser-based system in which we use the laser technology to measure the length and the radius of the tools. So, so I will just run a program here. So I have already written a program, and actually this we have got a bloom cycle. Uh, it is an inbuilt cycle on the machine. So we just have to set the parameters here. So also, so this is a program written manually, and I have just added the bloom cycle here. So I'll be starting it in a while. So before I start the cycle, I'll be removing some of the components loaded onto the work table. So I need to first take off these components here. Only then I will be able to run this bloom cycle. Just hold for a minute. Okay, now we can run this bloom cycle. So here I have a program for the bloom cycle. So I'll be discussing this program in the later session when we'll perform some machine operations. So for now, I'll be skipping that part and we'll be just running this program. Uh, and also here we have this bloom cycle pre-installed onto the machine, onto the controller. Just we enter some of the parameters here, like what we want to do. We want to measure what we want to measure. We want to measure length and radius. So I think the screen is visible to you. Uh, then we have which type of tool we are going to measure. Then there are other parameters. So we are not going to into much detail here. So just I'll be setting these parameters as I have already set the parameters required for the measurement of this tool. So here I'll just give an overview about the program as well. So here what I'm going to do, I'm going to measure the tool having a name, having a name of handmill 100. So we are going to measure this tool, and also here I have set the RPM of the tool as 1000 RPM, so 1000 rotations per minute, and also we have also the feed is taken by the machine as the default feed will be considered here. So I'll be just I'll also have a look to the tool list table. Okay. So we are going to measure this annual 100 tool, which is at the pocket number 2, and it has a length of 149.662 mm and a radius of 5.99. So it is actually already measured, but what we can do here, we will simply manually enter the values here so that we can confirm that the measurement we are going to do is different from the values already provided in the tool list table. So here we have a length of 149.662. So we are going to make it as so we just need to we actually measure the tool manually with the help of vernier caliper. So we are supposed to enter the approximate value in these blocks, in these columns, the length column as well as. So we are supposed to enter actually the length and the radius of the tool. The approximate value should be entered here. So first we'll measure the tool manually with the help of vernier caliper, and then we will enter the values here in this tool list table. So first I will just unload the tool. Simply I'll click the unload icon. Okay. So the magazine door is open now. So we'll hold the tool, press the button, and clamp it. Now we are going to measure this tool with the help of vernier caliper. So this is the distal vernier caliper. So this is actually quite accurate. So you can see here the reading is 0.00 mm. So what will we do now? We will first measure the length of the tool. So the complete length is actually considered here. So one end will be the surface which is touching the spindle, and the another end will be the tip. Okay, so we are supposed to measure it between these 2 points. So we are getting a value of around 138 mm. Okay, so the length, approximate length is around 138 mm. And also we are going to check the diameter of the bit, the end mill that is mounted on this holder. So the approximate value for the diameter is around 12.09 mm. Okay, I'm also going to check the length once again. So it's again coming to be 137.73. So we can take it as 138 mm. So the very first step is to we have to measure this length and radius manually. Then we have to load this tool onto the tool magazine. So we have to load this tool again. So first we need to provide the type of the tool. This type of the tool we are loading. So this is an admin that is already set. And then we have to enter tool name and other parameters. Then we will manually enter the length of the tool. So it comes around 138. So we'll be entering here a value of 138. And also the radius here will be around 6. So the diameter was 12.09. So we'll be keeping it as 6.1 I will take. Okay. So this is the radius for the tool. So now we'll be loading this tool. Before that, Just a minute. Okay, now we'll be loading this tool. Again, I'll click just the load icon. So Puppet number 2 is available. I'll press OK. Now we can see here the tool is loaded at the Puppet number 2, having a length of 138 manually entered, and also a radius of 6.1. Now we are going to measure this tool using the Bloom system. So I'll directly move to the program. So here we have a program for this. I'll simply execute this program now. Okay, so as per the program written, uh, there will be the RPM is set, and rest of the movements will be the default movements, because I already told you that this is a inbuilt cycle for the measuring system. Okay, the tool is now on the screen, having an RPM of 1000 rotations per minute. So I'll be moving it slowly, so you will be able to analyze what's going on. So it is actually moving towards a measuring system that is installed onto the machine. So if we can focus here, yeah, yeah. So this is actually the measuring device installed on the machine, and we call it as Bloom, BLUM, Bloom. So this is a uh, laser technology that is used to measure this different types of tools. So I'll be providing small fields, so you will be able to analyze what's going on. Focus. So, yes, side. So we'll be showing it from another angle. So we'll be doing it for few tools. So it will be clear for you. Now the radius is getting measured actually. Uh, Previously the length was getting measured. Now the measurement is over. Okay. So if the cameraman can focus the screen now. So we'll first have a look on this measuring system. Focus this portion now. Okay. So this is actually the measuring system called as Bloom. So actually, here is uh, there is a gap here. So the laser is coming out from one side, and uh, it is and the radius and the length gets measured. Also, we have some nozzles here that flows air so that the tool is first cleaned, then the measurement will be done. So we are not going into the principle of this system. That is a different part. We are actually confined here to the functions of the systems that are present on our machine. Okay. So this is the measuring system here. Uh, so the tool is as per the cycle. There is a movement in the z-axis. So this is the fixed point, fixed location that is already set on the machine. So this will be similar for all other tools. Just we need to change some parameters actually. So we need to set the parameters like what are the number of edges, where I want to measure the radius, and from which point I want to measure the length. So we just have to change these parameters, and rest of the movement, the speed, it is already set, but we can change the RPM here. So now we'll have a look on the main screen. Okay. So here, after after this measurement, the cycle is complete now. The cycle is over. So you can see here, we have a tool name as anvil 100, and also R implies here the radius. So the radius here is 0.000, and also the length is 0.000. Okay. So once I will reset, I'll press the reset button. These values gets updated. Okay. So I'm just pressing the reset button. Okay. So now here you can see we have got a radius of 5.99. And also the length here is 135.749. Okay. So we manually entered the values. For length we have entered 138 mm value, and for radius we entered it as 6.1. So now these are the exact measurements that our measuring system has provided to us. So here, we don't actually enter values manually, because this is a very precise machine. Here we have a least movement of 1 micron. So to maintain that accuracy, we have got this measuring system. Okay. For now, we'll also have a look on the work table. So here also these values are updated now. The length is now 135.749 and the radius is 5.99, which is the exact values of the tool dimensions. Okay. So this is how our measuring system works. How we measure the different parameters of the tool. Now we'll be also going to do it for other tools as well. Like we are going to do it for say facing tool. So facing tool is at the pocket number 8, and here the length is 140 mm and the radius is 31.634. So we just manually change the values here. We are not going to measure it now. by vernier caliper, because we know the values will be around 140. So we are going to change it as we'll be entering it as 142, and for radius, the actual radius is 31.634, but we are going to change it as we'll take it as 33. Okay, so now we'll be running a program for this. Okay, so this is the program. Here we have here we have just changed the parameters. Sorry. Okay, so here we have just changed some of the parameters like number of edges, because the tool which we are going to measure has got 7 cutting edges, and rest of the parameters are almost same, because we are going to measure here, we are going to measure length and radius, and also we are going to measure the same type of tool. So this is the default cycle. We are just going to run this cycle. I'll just press the execute icon here. Now we are on the main screen. Okay, I'm simply going to execute this cycle. So we will focus our camera to the measuring system now. Okay, I just pressed the start cycle button. Also focus on that on the blue. So first the length is measured, then the radius gets measured. So here now the radius is going to be measured. The cycle is complete. Okay, now focus on the main screen. Yeah, the cycle is now complete. As you can see here, again, this radius here is zero point 0 and the length is also zero point 0. And we have got a tool of dial 63 facing tool. So once I press the reset button, the values will be updated here. So previously we have entered values of around the length was 142, I guess, and the radius we entered was around 33 mm. Now I will just press the reset button and we'll see what are the results. Okay, so again here we have got a radius of 31.636. Okay, so this is the exact radius of that particular that particular tool, and also the exact length for this tool is 140.144. Okay, so these measurements are very much precise and accurate, because as I already told you, the least movement here is of 1 micron. So For that purpose, there are no chances of any approximate values that we can enter here. That's why we have got this measuring system installed on the machine, so that our there will be precision in our work, the accuracy that for that this machine is actually designed. So we'll also have a look on the work table. So here again, we have this tool. This time this tool is on the spindle. Okay, so everything is updated here. We have all the information here. So this tool is on the spindle right now, and has a length of 140.144 mm and a radius of 31.64. Okay, so this is how we measure different types of tools. Uh, then we have also some other tools like we have got drilling tools, we have got tapping tools. So I think we'll drilling or tapping tool because there we are actually measuring the length of the tool only. We are because the radius will be whatever it is, because in drilling or in tapping we have only got the movement in a z direction, in z axis actually. There is no movement in uh, xy direction, because we are just using these tools. If we talk about drilling, we are using it for drilling a hole. And if we talk about this tapping tool, we are going to make threads with the help of this tool. So once the point on the workpiece is located, then there will be movement only in z axis. So after after we start the cycle, there will be no movement. The tool will be uh, will be taken at the point where we want to make a drill, or where we want to make a thread. Okay, so after that it will move only in the z direction. Okay, so that's why. So here, if I'm going to put here any value for the radius, that will not make any difference to us, because whatever is the diameter of the tool, we will get the same hole size. Okay, because there is no xy movement, we are only getting the diameter whatever it is. I can enter here any value. Okay, so that will not affect the operation that I'm going to, the dimensions of the hole or the dimensions of the thread that I'm going to machine. So, so here for tapping tool, we can enter it as 5 approximately. The exact value is actually, we are, this is a M12 type of tap, having a diameter of the major diameter actually is 12 mm. So we can enter here directly the radius of 6, or I can make it 7. And also we are not going to measure it. We are not going to measure this radius actually. So I'll keep it as 7, and just I'm going to change this length. So it's 199.621. So I'll be making it as I need to provide the approximate values. I'll be providing here as 201 mm. Okay. So here we just for these types of tools, which which machine only in the only in one direction, I can say, whether it is z direction or uh, it will be only actually if I say, it will be only the z direction, whether my workpiece is whether my workpiece is parallel to Z axis, the top face. I can say I think I should explain it later so that you will be clearly understand this point. So here now I'm going to operate this cycle. I'll first reset the previous program, then we'll move to program manager. So here we have got a program for this tapping, for the measurement of this tapping tool. So we are only going to measure the length here. Okay, I'll be simply executing this program. Okay, first we'll focus the camera onto the screen. Okay, thank you, sir. Okay, so first we'll focus the camera. Now I will start the cycle. So this is the tapping tool which we use to perform tapping operation. So here we are just going to measure the length of the tool. So here we have only measured the length actually. We have not measured the radius. So that's why the cycle is complete. Uh, because if we wanted to measure the radius, then the tool could have moved in the x-axis direction, but this time, as per the cycle, it is not moving in the x-axis direction. I can say it will just directly move in the z-axis direction now. The cycle is complete actually. So here you can see again. You can see here that we have got zero values for radius and length. Once the reset button is pressed, these values are updated. So radius will be same as it is because I didn't measure it. So the radius will be same as 7 and the length is updated here. So I have entered it as 201 mm, but here the actual length is 199.615. Also, if we have a look on the tool list, so here also these values are updated. So I will manually change this radius here because this is actually a M12 tab. So the radius will be 6 mm. So for our information, we'll be keeping it as 6. Okay. So this was about the measuring system called Bloom. How we are measuring the tools and how we make these tools ready for machining. Okay, first we'll simply load the tools onto the machine and then we use measuring system to measure these tools and the measurements are quite precise, quite accurate here. So after that, now the tools are ready to perform operations, to perform machining. So before that, we'll be will be understanding the concept of work offset, and before that, we'll have a look on some of the important tools that are already loaded on the tool magazine. So we'll have a look, and because they have got different functions, uh, they are not actually utilized for machining, or they have got other functions. So we'll have a look on such tools. Then we'll proceed to our another topic called work offsets. So here I'm going to first unload the tools. Okay. Now, so we have got some special tools here. So we'll be discussing these two tools, which are not utilized for cutting. Okay. So this tool is called as a master tool. Actually, we don't use this tool to perform any machining or any of the operations. This tool is actually used to calibrate different uh, devices. Like we are calibrating our measuring system called Bloom. So this is called as master tool. We just use it for calibration. So actually, the exact dimensions of this tool are provided or written here. If cameraman can focus on the details that are written on the workpiece, sorry, on the tool. So here what we have got, we have a length of 100.013, that is L1, and that length is from this point to the tip of the tool. So this is called as length 1, and we have one more length here, uh, L2, which is equal to 10.011. Okay, so this length is for this part, for this cylindrical uh, attachment here, I can say. So the length for this part is 10 mm, 10.011 mm. Okay, so it's also given in the microns. Decimal points are there. We have got 3 decimal points. So actually, this is 10 mm plus 11 microns, the length for this part. Also, the length of the complete length is 100.013. Okay. Also, the diameter is written here as 12.002. Okay. So, what we do, we directly enter these values in the tool list, because we don't need any measurement for this tool. That's why this is called a master tool. So we directly enter these values, the complete length and the radius, in the work table, and we actually use this tool for calibration. So calibration of a measuring system needs to be done periodically. The bloom system that we are using to measure other tools is needs some calibration. So we are periodically calibrating this bloom system with the help of this master tool, because here we know the diameter of the tool, the exact diameter. So we have also got a calibration cycle on the machine. So we simply we just run that cycle, and the measuring system gets calibrated. Means the measuring system, because the machine knows that this is the exact, this is the correct dimension, this is the correct information that we are providing to the machine. So the machine changes its measuring mechanism accordingly. Okay, so it adjusts, it can it just adjust different parameters, because this radius is correct. Okay, also for the length, so there also for if we talk about the length, that is also used for the calibration, because this length is the correct length that we are telling the machine. So also we use this master tool to measure one more tool, or I can say device, to calibrate one more device that is called probe. Okay, so we have got some procedure, some cycles that we need to follow to do such activities. So for now, I'll be showing you one more device that's called probe. So this is an electronic device actually. We call it as a probe. Okay. So this probe is used to set work offsets onto the machine, or we can say we can measure the dimensions of a workpiece with the help of this probe. So we are using this technology because we need accurate measurements, accurate dimensions. So here we first calibrate this probe. What calibration I mean to say is we can't measure the length of this probe using the measuring system, the bloom. So for that, we are using, we measure the length of this device using the master tool. And we call this as the calibration. The calibration process, I can say. So we measure the length and the radius of the probe with the help of, only the length is measured with the help of master tool. But if we have to measure the radius of this ball, actually, there is some other procedure we need to follow. So master tool helps to measure the length of this probe. Okay, so this is simply, I can say, an electronic device that we are going to use for the precise measurements of the workpiece, as well as we'll be setting work offsets onto the work piece that we are going to machine. Okay, so these are some. This is actually a very costly tool. So this is out of all the tools, this is the costlier one. So we'll see how these tools work. and also we have kept these tools in the fixed pockets. Okay, so here we have pocket number 29 and this is pocket number 30. So once we call this tool, I can say probe, and after completing the whatever I need to take the work offset or I need to take the dimensions, after completing the process, this tool will be loaded automatically on this fixed pocket. So these two pockets are fixed. Okay, and it is similarly for master tool. After we use it, then it will be again put on this pocket, pocket number 29, and it's also fixed for it. So for now, uh, we'll see. We'll move to another topic, which is called as work offset. Uh, we'll uh, we'll continue in a minute. I need to make some arrangements here. So just I'll be back in a minute or two. So now we are going to have a look on this work offset. What work offset actually is. So as we already know, we have some coordinate systems that are available, that are that we need to work with, and we are machining using some uh, tool, or I can say machine tool, to perform some operations. So we have actually got, in general, I can say we have got two types of work offsets. Uh, we have a machine coordinate system. Okay, so also we have work coordinate system. So every machine has a fixed machine coordinate system that tells us the home position or the reference position of the machine, and that is fixed for every machine. Uh, but if we talk about work coordinate system, we can have a number of work coordinate systems available as per our job. So I can conclude here that we can have one machine coordinate system, but we can have infinity number of work coordinate systems. Okay, so this machine coordinate system is fixed. Uh, so here you are actually these positions are the actual values of the machine where our spindle is presently. So presently our spindle is at minus 632.570 mm in x-axis. Okay, so this value is from the origin point, or I can say from the machine coordinate points. And also for y, we have a value of minus 5.2. So this is a present position of the tool or spindle. Likewise, Z is at the position of minus 1. So these values are measured from the fixed point, the machine coordinate system, which is fixed, and I can say it is a permanent position. So what I'm going to do, I will bring this spindle to the home position so that we can understand this concept clearly. So I'm directly going to, so these are actual values that the machine have. If I highlight this icon, then I get different values. But these values are the values as per the work offset set on the machine. So we'll have a look later. But first, what I'm going to do, I will bring the spindle to its home position, or uh, at the origin point of the machine, which we call as machine coordinate system. So I will directly, so I'll first unload the tool which is on the spindle. So we have unloaded the tapping tool that was on the spindle of the machine. Now our spindle is at this position. Okay, so this is actually the tool changing position. So these values are the actual machine values. These values are measured from the home position of the machine. So now I'll bring So I am going to bring the spindle to the home position manually. Okay. So here I am only moving in the x-axis direction, and that is actually the positive x direction. So there are two directions for every axis actually, the positive and the negative one. So this time we are moving in the positive direction. So here, and also we'll try to focus the camera on the spindle so that it will be more clear to you. So this is the, so I am actually moving the spindle only in the x-axis direction. I can increase some speed here. So this is the x-axis direction, and this is the positive x-axis direction. But if I am moving to the left side, that will be the negative direction, and this will be the positive direction for x-axis. Okay. So we'll first bring the spindle to the home position at x-axis. Okay. Now the spindle is at home position in the x-axis direction. Is this one? Yeah, this is the home position for the spindle. Now we'll be moving this y-axis. So we are manually moving the y-axis. So the spindle is moving away from the we have reached the home position in y-axis. Then we are going to bring the z-axis at its home position. Okay. Now, now the z-axis is also at the home position. So this is the origin, or I can say the home position for these three axes x, y, z. So this is actually the machine. These are the machine coordinates, or I can say this is the machine coordinate system. That is that tells us the coordinates of the machine from which we may the measurements are actually provided. Say for example, if I give a value of 100 mm in x-axis, then the spindle will move. So it depends whether I want to move the spindle as per the machine coordinate system or as per the work coordinate system. Okay. So here, if I am giving a values as per the machine coordinate system, the this point will be the origin, will be the home point from where the values are applied, or from where the values are set onto the spindle. So this is similar for all the other axes as well. Like for y-axis, if I am giving some value, it will consider this value. So here I am just giving some values here. So if the measurements are as per the machine coordinate system, then it is in the negative direction. Okay, I can say that only the negative values are provided because the starting point is 0.100. So it will be it will the maximum travel, as I already discussed, is 650 mm for x-axis, and for y-axis it is 520 mm, and for z-axis it is 475 mm. Okay, so the machine, so the machine coordinate system tells us the origin point. So here I can see, as I already showed you, that this is the home position. So the spindle will now move on the left only, on the left side only, or I can say it will move towards the front side, or if we talk about z-axis, then it will move downwards only. So this is the extreme point. So the spindle is not going to move on the positive axis, positive x-axis now, not in the positive y-axis direction, and not even in the positive z-axis direction. So the maximum point is reached now. So it will only move to the left if I talk about the x-axis, and it will move downwards if we talk about z-axis, and it will move towards the front side if we talk about the z-axis. Sorry, the y-axis. So here, what I'm going to do, I will manually enter some values here. So I am just giving some commands to the machine, like G0, G90, G53, X minus 100, Y minus 100, and C minus 100. Okay. So once I execute this command, these codes, you will see here that the machine is giving the information that we have to go. The machine is telling that the distance to go is minus 99.9. Okay, because I have given a value of minus 100. So already the machine is at 0.1. So this 99.9 is the distance that the spindle needs to travel. Okay, so it is in the x-axis. Similarly, also for y-axis we have got this value, and similarly for z-axis. Okay, so you can see here, once I will increase the speed here, the values are getting changed. Okay, so here you can see it is moving in all the three axes simultaneously. Fine. Now we'll focus on the spindle so that you will observe. So see here, the movement to the spindle is in all the three directions: x, y, and z. So this is the point. This is the position which we have entered here. So this is the position where we have the values of 100, minus 100, minus 100 in the y, and z also. Okay, you can see on the screen we have reached this point. Okay, so now I'll be separately moving these axes. We'll only move x axis first. Okay, I'll simply start the cycle. So now the spindle is at minus 100, and the distance to go is minus 100. Okay, so once I provide some speed, the spindle starts moving, but only in the x-axis direction. Okay, now we'll focus on the spindle. as you can see here. So this is the point where we reached our values that are provided to the machine. I'll also again change it. I'll make it as I can say 400. I'll start the cycle again. Okay. So this is the point you can see on the screen now. So this is the position, uh, current position of the spindle as per the actual values of the machine. Okay. So in x-axis direction, the position is the spindle is at 400 mm. So if I talk about this negative sign, as I already told you, that from the home position, our spindle can move only in one direction from the home position. That's why we kept this as the negative sign is provided here. But actually, what we are doing here, if I am moving more towards the negative part, if I am moving to minus 500, say, so the value is actually getting decreased in the negative side, I can say. Okay, so if I have a value of here 100 mm, negative 100, so we are actually moving to the positive side. If I am moving from minus 400 to minus 100, then I can say we are moving in the positive direction. Okay, likewise if I am moving from negative 100 to negative 400, so we are actually moving in the negative direction. So likewise, so for machine, you will see this negative sign is always present. But if I talk about this work coordinate system, you can see there we have totally different values. Okay. So now what we are going to do. So this is similar for other axes as well. Like we have got C and B axes here. Okay. So here also, this time the C is at the origin, at the home position, okay, and the B is also at the home position. Fine. I can also provide some rotation to these axes. I will simply change the command to C 90 and B 50. Okay. Let's see. B. Hello, am I audible?
Yes, sir.
Yes, sir.
Okay, fine. So now we'll be providing some uh, rotations to C and D axis only. Okay, so I'll just start the cycle. So I have provided the angle of 90 degrees for the C axis and the angle of 50 degrees to the axis. So I'll just start the cycle. Okay, so you can see here distance to go is, so there is no movement for the these three axes XYZ. We are only providing the moments to the C and D axis. Okay, so distance to go. So the 89.827 is the rotation that will be that we need to cover for C axis, and 49.904 needs to be covered for D axis. Okay, so I'll just give some key. Okay, so these values are changed now. Okay, so here you can see there is no sign for these two uh, axes, and here you can see the plus sign for C and also the plus sign for B. Means this time the rotation is in the positive direction. Okay, so C axis is moving in the positive direction. So the clockwise movement of the clockwise rotation for the C axis is the positive direction for C axis, and the negative direction is for counterclockwise direction. Likewise for B axis, if the B axis is moving in the clockwise direction, then that will be the negative direction for the B axis. But if it is moving in the counterclockwise direction, then that will be the positive direction for the B axis. Okay. Now we will focus the camera on these two axes so that we will you can analyze what's going on. So so here you can see that the C axis. So I'll again repeat here. So this is the C axis. Uh, this table rotates about z axis. Okay, so that will be our c axis, and if the rotation is like this about y axis, then that will be our b axis. So this time I am providing the angle to this table. Okay, actually the c axis is moving only in this direction, okay, in the clockwise direction. So I have provided the angle of 90 degrees, the positive 90 degree. Okay, that's why this table will rotate uh, in the clockwise direction. Fine. Also for this d-axis, I have provided the angle of 50 degrees, but in the positive direction. So it will rotate in the counterclockwise direction. Okay. So for c-axis, the clockwise direction is the positive direction, and counterclockwise direction is the negative direction. But for b-axis, it is the opposite to the c-axis. Okay. So here actually the c axis is moving in the clockwise direction, but it is tilted because of this d axis. Okay, so I think I'll be moving first these axes separately, then we will provide a simultaneous movement. Okay, I'll just change it as I'll just cancel the cycle. Okay, so I'll be only providing movements to the c axis. No, no. Again, the B and C axes are at the own position. Now I'll be only providing rotation to the C axis. So you can see here only the C axis is rotating in the positive direction. I will provide some more rotation to the C axis. We'll rotate it to 180 degrees. Okay, fine. Now we'll be moving this B axis as well. So this is the positive rotation provided to B axis. Now we can see here on the screen. You can see here the C axis is at the position 180 degrees and the B axis is at the position 50 degrees. Okay. So these are actually the actual values of the machine that we are providing to these axes. So this is all about machine coordinate system, but we have got one more system called work coordinate system. So if I change these values according to the work coordinate system, then we can observe here that the position of x-axis is changed similarly for y and z also. Okay, but for c and d it is same. So actually, here we have not provided any work offset in these two directions, but we have provided work offset only in x, y, and z. Okay. So here I will manually just enter some offset value on the work offset table, and these values will be changed automatically. Okay. So say I'll go to work offset table. I will manually enter some value here. Say 20 degrees, and for this 30 degrees. Okay. Okay. You can see here now that also for C and D axis the values are changed. So you can see here C axis is showing a value of 160 degrees and D axis is showing a value of 20 degrees only. So if I see the actual values, you can see here these are actually the as per the machine coordinate system values, and these values are as per the workpiece, the work offset, the work coordinate system. Okay. So I think it is the time is over actually. So I think we will continue the rest of the topics in tomorrow's session. So if you have any questions, we'll be giving you some minutes you can ask till now, but our topic is still not completed actually. We'll be continuing this topic tomorrow because it will take some time. So it's better to uh, continue it tomorrow. So we'll be able to understand this concept clearly, and this is actually the very important concept which we are supposed to understand clearly. Okay, so we'll be stopping here today. So we'll continue this topic hopefully tomorrow. Till then, take care. And if anyone have any questions, you can they can ask. Thank you so much. Sure.
Any questions? Thank you, sir. Thank you so much.